Consider a block of mass, 14.5 kilograms, being pushed up an incline by a horizontal force of 154 newtons. Initially, the block is moving with a speed of 1.2 meters per second, and after the block has been pushed a distance of 6.25 meters on the incline, it moves with a speed of 3.3 meters per second. Letter A. After the block has moved the 6.25 meter distance along the surface of the incline, how much higher is it than its initial position? And letter B. Determine the magnitude of the frictional force acting on the block. So I've already created our free body diagram for the block of mass in this scenario on our ramp, which is what you can see here. I've labeled my free body diagram with those forces. I've also included my coordinate system to clarify the direction of my X and Y. And then on the left-hand side, I've also written down all of the knowns that I know and my two unknowns, aka A and B. So we want to use this free body diagram as well as our understanding of mechanics to determine the height that was traveled by the block in letter A, and then to determine the frictional force that's opposing this applied force's motion in letter B. So for letter A, to determine the height traveled by the block relative to its initial position. At the top left, I just have our free body diagram there with our knowns and unknowns again. And then over here on the right-hand side, you can see me solving that question. And I just wanted to talk through the thinking. So we know this angle, the elevated angle of our incline is 25 degrees. We know the distance traveled of the block on that inclined slope was the 6.25 meters. So essentially, we know our hypotenuse and we know our angle, and we want to find one of the legs, in this case, our y leg. So we know SOHCAHTOA, sine of 25 will equal delta y over delta d. I can reorganize that for delta y, and that'll give me delta y equals delta d sine 25. Plug in our values, and I got 2.64 meters for delta y. So that's the answer, or at least what I got for letter A. And then for letter B, we're trying to determine the magnitude of that frictional force. So once again, here is our free body diagram with a list of knowns and unknowns. And so if we look at our free body diagram, hopefully we recognize that the frictional force is acting in the negative x direction. So since I've defined positive x as up the ramp, friction right here is obviously going to be opposing that motion, so it goes down the ramp in the negative x direction. So applying Newton's second law of the sum of the forces will equal mass times acceleration. Here up at the top is the sum of the forces in the x direction, and I've written down all of those forces from my free body diagram. So we have the F applied x. This horizontal force exists both in the x direction as well as the y direction. So in my sum of forces in the x direction, I have to include the x component of that applied force minus the x component of gravity, which is right here. There's going to be a little tiny negative x component from gravity right here, minus the force of friction because it's in the negative direction. And we know that those forces added up will give us a net force, and that net force does cause acceleration. So that will equal m times a in the x direction. We can then reorganize this equation to solve for a frictional force right here. And then I've also included these two little triangles. And I got these two triangles, our F applied triangle and our FG triangle. I got those just from looking at our free body diagram to just clarify, to break it up into those components. Because then I can essentially do the SOHCAHTOA to determine that F applied x is actually F applied cosine of 25, and so on. You will then run into a problem with this scenario of recognizing that we know m and we know g, but we don't know acceleration. And since I'm running out of time, I've decided to utilize kinematics to find that acceleration over here. I've then plugged in that acceleration into this equation to solve for our frictional force.